All right, we're here. This is like the holy grail of Calculus 1 content in general. So I want to jump right into it, but real quick, I want to recap what we've been doing over the course of this chapter. So we started off by talking about antiderivatives, or indefinite integrals. So we were sort of looking at how to work backwards from the process of differentiation. Okay, fair enough. Then we jumped to talking about definite integrals. And based on the way we were doing things, we didn't really see an awful lot of relation. This was like a purely geometric thing in terms of areas. Then we saw how to do it using those Riemann sums. But it didn't really connect to, the indefinite integral stuff. The only things they seemed to have in common were the notation and the, name, integral. So as it turns out, the second part of this thing we call the fundamental theorem of calculus kind of brings these two guys together. So let's do it. All right. So the big idea here, again, fundamental theorem of calculus, that's kind of my standard abbreviation for these things when you've seen stuff like mean value theorem abbreviated as MVT before. Hopefully that makes sense. Anyway, so usual setup, we've got a function, we're assuming it's continuous. So, and we want it to be continuous on a closed, bounded AB interval kind of thing. You're kind of standard at this stage. All right, as it turns out, now we can move on to the punchline. That's all we need to know hypothesis-wise. So, as it turns out, to evaluate this definite integral, that's all we need. Where this capital F that I've written is any antiderivative of f of x. Any antiderivative. So instead of having this weird Riemann sum thing where we were having to take a limit of summations of rectangle areas and whatnot, we can find an antiderivative, evaluate it at 2 points, and take a difference. So let me, can't spell, I'm so excited. Any antiderivative. So we don't even need to worry about the plus c. We can just say, we'll pick the one with c being 0, and it's gone. So, yeah, this is a really, really big deal. This is the sort of thing that I've known professors who, when they get to this in a calculus class, they bring a boombox with them and play the Hallelujah chorus when they get to this stage. This is huge. This particular move comes up often enough in what we're going to be doing for the remainder of the course. I usually shorthand it like so. So again, capital F of x with this kind of vertical bar at the end. Some textbooks use like a squared off bracket. I don't like that. I prefer the vertical bar. But yeah, so that's that. So that's all the fundamental theorem of calculus says. It's short, it's to the point, and it is freaking awesome. Okay, so let's take a look at some of our examples. So I say some, I mean one in this instance. I'm going to let you revisit another one, on your own, where you can invoke the awesome power of the fundamental theorem on it. Okay, so going back. So before, we worked this thing out using a limit of Riemann sums, and I think I filled up this board at least once, probably twice, getting to the point where we had a value for this thing, so we can actually compare it to what we came up with before. The fundamental theorem is going to save us so much work here. I am not even joking. We need an antiderivative of this thing. So we spent the entire first section of this chapter doing precisely that. Our friend the power rule says we add 1 to the exponent, divide by the new exponent. If you had done 2 times 1/4 and called it 1/2, totally understandable. An antiderivative of 1 is simply the variable x. All right, so we got that guy. We evaluate him at 0. We evaluate him at 5. Technically, we start at 5 and then subtract what happens at 0. So I plugged 5 into this thing. So 1/2 times 5 to the 4th plus 5, okay? Minus, again, remember that minus is important. It's baked in here, even if for this example it turns out it doesn't, have much of an impact. If I plug 0 into this thing, yeah, I get back 0. So, all right, so way faster. 5 to the 4th, you can check at 625, however you get at it. So we have 625 over 2 plus 5. That should look really familiar if you jump back to the video on Riemann sums where we worked this sucker out the long way. 635 over 2, the same thing we got back then. Sweet. And for what it's worth, when you've been at this for a while, you don't even necessarily have to be quite this careful. You might be able to jump from this to this, done. So, party on, Wayne. All right, let's take a look at a new example. As I said, I'm going to leave the other guy, the quadratic that we looked at, as an example for you to tackle in the assignment, just so you can revel in the power that this ends up putting at your fingertips. All right, so let's do something a little more involved. So I've got a cube root function floating around out front of one of these guys. So remember, no product rule to get an antiderivative. Turn this thing into x to the 1/3 and distribute. So again, calculus is easy. It's algebra that's hard. So I would get x to the 4/3 plus 2x to the 1/3 once I make this the fractional exponent, split it across. Now I need antiderivatives. I add 1 to this exponent. 4/3 plus 1 would give me x to the 7/3. Dividing by 7/3 is the same thing as multiplying by the reciprocal, the 3/7. All right, here, adding 1 to that exponent would take me up to 4/3. Dividing by 4/3 is like multiplying by 3/4. Don't forget that 2 that's hovering around out front. Evaluated at 1, evaluated at 0, take the difference. So plugging in 1 here, the x goes away, I've got 3/7. Plugging in 1 here, the x goes away, I have 2 times 3/4, which is 3/2. Plug in 0, everything vanishes in a puff of logic. So I've got 3/7 plus 3/2. If you find a common denominator, put these together, I got 27 over 14. If you'd had a decimal, I'm generally okay with that. But so that's what you're looking for. Again, super duper quick. We spent about as much time explaining the algebra as to how we got to that thing as we did, cranking out what the fundamental theorem told us we should get. So yeah, I really like when we get to this part of the course, and generally my students do too. All right, one more example, and then we'll call it a video before we talk about something else. Okay. So, I want to do something involving some trig functions, also where we need to be a little more careful and we don't have a limit of integration that's 0, so that part just kind of gets taken for granted. All right, so I'm also going to mix up the variable because I like doing that. All right, so 2 sine of theta plus cosine of theta, letting theta go from pi over 2 to pi. Fundamental theorem says we need an antiderivative. So antiderivative of sine of theta is negative cosine of theta. So negative 2 cosine theta. Antiderivative of the cosine function is sine of theta. Again, please don't forget to write the the of thetas on these things. So all right. So now I need to evaluate that thing at pi over 2, and then take the difference. All right, so I'm going to be a little careful here. So negative 2 cosine of pi plus sine of pi minus, sorry, I'm short on space here. I'm not going to try to wedge that in. So we have negative 2 cosine pi over 2 plus sine of pi over 2. Okay. Now, by design, if you evaluate these things in your calculator, make sure you're in radian mode. Remember, we do calculus with radians, people. Anyway, so the cosine of pi is negative 1. I'll fill that in a minute. The sine of pi is 0. He goes poof. By the same token, the cosine of pi over 2 is 0. He goes poof. And then the sine of pi over 2 is just 1. So we've got -2 times -1 that we get when we work out the cosine of pi, minus, because the minus is baked in, remember that, the sine of pi over 2, which is 1. -2 times -1 is, +2. So in true mathematical fashion, I found a really, really long-winded way to write 1. So that's a few examples. I'm going to kick off the next video with another one, but I'm going to use it as sort of a springboard to take a look at another topic. So don't touch that dial. Wait, do you know what a dial is? Oh, now I feel